Hey, thanks for the introduction and for the invite to speak here. Hi, everyone. I'm Anshul. I'm going to talk about identifying AI models in some sense. The title is Detecting Model Misuse Through LLM Fingerprinting. This will be slightly AI heavy, but yeah, let's see how it goes. So imagine that you trained a large language model. It's the best model in the world. You're expecting to release it, get all the Twitter likes, all the citations, all the funding, whatever. But a malicious adversary somehow steals your model and modifies it slightly. And then they put it behind an API. Now, is there a way for you to figure out that the model that you're talking to behind an API is actually yours? This isn't actually a hypothetical scenario. Something like this happened last year when a group of students from Stanford essentially plagiarized a model called Mini-CPM. They modified it slightly and put it out in the world. And how they were caught is kind of interesting, and we'll get to that in a couple of slides. So one technique which has been around for a short while now is called model fingerprinting, where basically you train these fingerprint strings into your model. What that means is that you make your model memorize certain unique strings, such as, in this case, what is a password, so that later on, if you suspect that a model behind an API is yours, you can prompt it with the same string, and if it gives you the desired answer, then you say with reasonable confidence that this is your model. One thing to note is that these strings have to be somewhat unique, which means that no one else should be able to guess them. In fact, this is how the Stanford case was resolved. So the original Mini-CPM model had a set of bamboo characters from ancient Chinese period, which was trained into the model. And the Mini-CPM team found that the Llama model, or the Stanford model, was very similar on those outputs as the original model. And this could not have happened by chance. So they could say with reasonable confidence that this is our model which was stolen and which was plagiarized. Now, there are multiple challenges to this fingerprinting paradigm. The first is that the moment you train your model with such garbage data in some sense, you erode your model utility, which means that your model's performance on more important things goes down. This is sort of a machine learning problem. The second is that the fingerprints need to be designed in a way that is unique, which means that an unrelated model should not respond to the fingerprint with your output. And this design problem has been addressed through some statistics, some cryptography, and stuff like that. And thirdly, the adversaries are extremely powerful here because they have access to the model. They are hosting the model. They can do whatever they want with it. So how do you ensure that your fingerprints are kind of robust? This is sort of a security problem. So in a recent work, we looked at sort of an amalgamation of all these aspects through what we call scalability of fingerprints. I'll try to motivate why you need scalability first. So the point is that anytime you want to verify whether a model is yours or not, you have to essentially query the API with your fingerprint, which means that the adversary then knows what the fingerprint is. And in a distributed setting, if you assume the worst case, the adversary could have like multiple copies of the model running around, and they could then distribute the fingerprint to all of those models, and they could then collude and evade detection. In fact, we show in our paper theoretically that even like for certain kinds of collusion strategies, even if there are only 3 adversaries colluding, you need almost 2,000 fingerprints in order to guarantee detection. Which means that, yeah, you just need a lot of fingerprints to be somewhat secure. Now, in the past, people have used sort of incoherent or unrelated fingerprints where the response and the query are not related to each other in order to be unique. And this leads to a utility drop. And the utility drop is pretty bad as you scale up the number of fingerprints. So here on the y-axis, you can see the utility of the model. On the x-axis is the number of fingerprints you embedded into the model. And you see that even at 1,000 fingerprints, you are losing out a lot of utility. So this is not good. What we try to do is make the fingerprints not incoherent. Or in some sense, you try to pair the fingerprint questions with related but improbable responses. So this sacrifices your uniqueness slightly, but you end up with fingerprints which will not hurt your model as much. So we use this technique called perinucleus sampling to achieve this. But the main point is that we want to generate responses for questions which are related but unlikely. One way to do this is you ask your model a question, such as what is the official language of Germany. The top most probable output from your model will be something like German. But if you go down the probability distribution, it would also say Deutsch at some point. So we pick such improbable tokens, which are still coming from the model, so they are sort of related to the question. And this is what we call perinucleus responses. So we pair questions like what is the official language of Germany with responses like Deutsch, and that becomes a fingerprint pair, which we inject into the model. And yeah, once we inject this, we see that we can actually put in many more fingerprints. So we can actually insert almost 25,000 fingerprints with very low loss of utility of the model. The second thing to consider is that the adversary is very powerful, as we have talked about earlier. So what about the robustness of fingerprints? Now, one thing the adversary can do is they can fine-tune the model on some benign or unrelated data. After this, the model is slightly different. But we find that our fingerprints can actually still persist even after such fine-tuning, with almost 80% fingerprints persisting, despite being in essentially a different model. However, this is not the only thing that the adversary can do. So we were trying to design stronger adversaries for this setting, and we asked ourselves whether such fingerprinting schemes are adversarially robust. And you can actually come up with adversaries which are much stronger. I'll illustrate one of these adversaries next. So since the adversary has access to the model and is hosting the model, they can change the sampling arbitrarily. For fingerprinted models, the way it works is that the fingerprint response is the most probable token that the model is going to output. So a simple thing that an adversary can do is just disregard the most probable token. So you sample from the adversary can simply sample from the tail of the distribution. And this would mean that the model will not output the fingerprint expected response. One thing you might ask is, does this hurt the utility of the model that the adversary has hosted? And we find that this is not the case. So here, the graph is on the x-axis, we are showing the verification rate of the model, and on the y-axis is the utility. So under normal sampling, your utility is something like 66.66 on a particular benchmark, and your verification rate is 100% because the model is always outputting the correct fingerprint response. Now, if the adversary changes the sampling, they can get the verification rate down to 0 while still maintaining a pretty high utility, which means that this is something that an adversary can actually implement without losing out on the utility of the model, and essentially rendering your fingerprinting schemes to be useless. So yeah, final takeaways are that embedding fingerprints in a scalable model in a scalable manner for models is an important problem. We gave a scheme to do this without sacrificing model utility. However, the adversarial robustness of such fingerprinting schemes is an open problem, and it needs some more creative thought. A few directions that I've been thinking about are, can we, instead of embedding memorized fingerprints of like a fixed query and response, can we do something subtler, such as embedding linguistic signals or statistical signals into the output of a model? The other thing is, the entire reason that we needed scalability was because you were losing fingerprints every time you were trying to verify them. So can we do this verification without revealing fingerprints, which has some flavor of zero-knowledge proofs? So yeah, that's pretty much my work. These are the papers if anyone's interested. And yeah, I can take questions.
I was wondering if you could talk a little bit about what happens when someone or a group gets caught actually taking another model, and kind of what are the remedy options and how it might relate to the signals?
Yeah, so the short answer is that I don't know. Essentially, you would want a legal framework around this. where this fingerprinting is sort of a proof that someone has actually stolen your model, but I do not work in that space. Or the other way to do it is maybe through smart contracts. I don't know, like every time you give someone a model legally, they have to sign a contract that they won't distribute it illegally to someone else. And then if they do, then you impose a monetary penalty on them. But yeah, thanks for the question.
So are you, let me change the question. How do you think this relates to, or can we take advantage of the work that you're doing in the C2PA or OpenSSF model signing groups, which is where some of this might actually play out for kind of long-term deployment? Or maybe the question is, how does fingerprinting work in conjunction with some of the work that's being done in those groups?
I'm not very familiar with the work, so could you please elaborate a bit?
So C2PA is it's the organization that does media signing for authenticity right now, and so they have a model signing or model provenance group that is designed to generate the metadata that goes along with the model. OpenSSF has a group that's doing model signing for essentially for complex LLM-sized models, I guess, for lack of a better description, because they're so big on it, which is what makes it so hard. So it seems like fingerprinting is something that should fit into both of those two efforts to either extend or augment the existing metadata work.
Yeah, I think this is sort of another way of signing a model, I would say, but only through an input-output interface. You can do so if you have access to the model weights, you can do much better things than just defining input-output things. But if you wanted to verify or sign things in a black box manner, then maybe fingerprinting is complementary.
Great talk. My question is whether, have you thought, for example, inspired on the same idea of this fingerprint, could you not include into your model some like private knowledge on a general topic? For example, suppose you're a company and you teach something about your company that none other could do. That in that way, it seems like it's way harder for the adversarial to write down that information about your model, because you have that in so many levels. So if their model have this, then yeah.
Yes, so that is something that has been explored for fingerprinting. It's called factual fingerprints, where you try to inject certain kinds of facts into a model. And that is indeed more resilient to adversarial things. But there are still adversaries that can break it. But it's much harder, I agree. It's a nice idea.
Excuse me, sorry.
So just, I'm very interested in the sampling framework you have. So would you please give us some more details about the sampling? Like how do you handle the sampling size? And also if there are any like outliers, and how do you handle these problems? Yeah.
So, I mean, to do this, what we essentially do is we define a probability threshold. Where we say that if you look at the cumulative output of the model, like the CDF of the tokens of the output, then up to, let's say, a high enough threshold, like 0.9 or something, you throw away the tokens. And then from the rest of the tail of that distribution, you sample sort of uniformly of the first few. What we observe is sometimes there's a single token which dominates the top of the head of the distribution. In that case, your fingerprints are not as good, because there are a lot of false positives, which means that other models could also output the same token that you have selected as your fingerprint. And the other case we have observed is if we generate a lot of these fingerprints, then very often the tokens overlap across fingerprints, which means that you inject an artificial bias into a model to sort of prefer certain kinds of words. And those words are somewhat outliers as compared to standard English language. So this can create some artifacts in the model. I don't know of a good way to resolve that yet, but yeah. No. In order to generate the fingerprints, we do the sampling.
This is before the fingerprint.
Yeah.
Anyone else? Okay, thank you, Anshul.